Welcome back. We're here for our second lesson of chapter 3. This is absolute extrema, meaning absolute maximum or absolute minimum. So what do we mean by this? Well, let's look at a picture first of all. If you take a picture of this unusual piece of a function, you can see that you have 3 points that I've labeled. Clearly C is the lowest point. And the way we say it is the minimum, the lowest, the minimum value is -1. That occurs when x is 3, or another way of saying it would be that minimum value of -1 occurs at the point C. And so when we're talking about absolute minimum, that's what we're talking about, the number -1. The highest point on the curve is B. This y value is referred to as the maximum value. The language is you say the maximum value of this function is 4. It occurs when x is 0, or you can say it occurs at the point B. So that's just the language. Now, when we move to a function that looks like this, which is really like a piece of a polynomial function, I've just limited it. I've stopped it, and I'm only doing the function starting when x is -4 and ending when x is +5. And if you look at this piece of a polynomial function, you can say that the maximum value in this particular function is the number 6. It's the highest. And it occurs when x is equal to 5 at the point 5, 6. The minimum, that is the lowest value on this function, is occurring at point C. The minimum value, -8, occurs when x equals 3. But this is language. This is called the absolute minimum. But this point can also be called a local minimum. So don't confuse the two. As it turns out in this function, the local minimum point actually is the point that coincides with the absolute minimum on the function. You notice the point B is called a local maximum, meaning the neighborhood. B, when y is 3, is the highest value. But for this function, the absolute highest point of all occurs at D. The highest value we see is 6. So this is the absolute maximum point. This point occurs at the absolute minimum. Sometimes the local max or min turn out to be the absolute max or min, but not always. So now we turn to our worksheet and we look at the first example. And you can basically see that the absolute max or min is going to occur at either the endpoints or the local maxes or mins. And so what we want to do is, if we take the first example, and I'll go back to what's above it in a minute, we have g of x is the function 2x cubed minus 3x squared minus 12x plus 2. And we're told to find the extreme values on the interval between -3 and 3. Now, I don't know what the function looks like, but what I basically want to do is find out the y values for the extreme point at the left, the y values for the extreme point at the right. So we want to find the y values for the endpoints. And so we let x be -3, and you can sub it in. Let's see, because I worked this out already. The y value works out to be -43. That's if I sub it in here and I get 2 times -3 cubed minus 3 times -3 squared. For the sake of time, try and get this video not to be too crazy long, I'm trying to work out some of these values ahead of time, and that works out to -43. Now you let x be 3, and this time you're going to do the same kind of calculation, only you're working with a +3, and what you end up with is -7. Now, I want to know if there's a local max or a local min in this function. So I find the derivative. When I find the derivative, I get 6x squared minus 6x minus 12, which is, which factors, take out a 6, and you're left with x squared minus x minus 2, which is x minus 2, x plus 1, and it neatly factors. Now we know that there are potential maxes, local maxes or local mins, where the first derivative equals 0, which occurs when x is 2 and when x is -1. Now the truth is, I can assess with our little table whether or not these are local maxes and local mins. The truth is, I don't really care, because they will be a turning point. And all I care about is whether that turning point occurs at a higher or lower value than the endpoints. So what I'm going to do is say, I don't really care what it is. It's a turning point of some sort. It's a flattening. It doesn't matter. I'm going to figure out the y values that go with these potential turning points. And so when you let x be 2 and you sub that into the original function, you would work it out, and the y value would work out to be -18. You then do the same thing when x is -1. You work out the y value. These are local maxes or local mins. 2 times -1 cubed, -1 squared. And when you do that, the y value works out to be +8. Now, I'm going to do a sketch, but the fact is you don't have to do a sketch, but it'll just make the point clear. I found the y values for the endpoints. So that's the equivalent of these 2 points. But in our function, -3 is way down here at -43. It's pretty low. Positive, let's see, -1 is up here at 8. The y-intercept is going to be at 2. And the value when x is 3 is -7. And the value when x is -1 is, 2 rather, is at -18. So now you can sort of see what's happening. This must be the graph. Sorry, it's a little bit awkward. But the point is, it gives you a visual that you can see. Here's one endpoint. Here's a second endpoint. Here's the local turning points. Clearly, -43 is the absolute minimum value. It is the lowest. And clearly, the absolute highest value, maximum value, is occurring at 8. Did I need the picture? No. Because once you have your 4 points, the 2 endpoints and the 2 points where the derivative equals 0, you can simply look at the y values and say -43 is the smallest and +8 is the biggest. And this occurs at the point -3, 43. This occurs at the point -1, 8. So I know what the lowest or highest values are, and I know where they occur. Now I'll go back and revisit this handout to show you the algorithm that's given here. Basically, if you want to find the maximum and minimum, the extreme values, number 1, find the derivative and find all points in the derivative where f prime equals 0. I'll come back to this later. So that's what I did. I found the derivative and where they equaled 0. I evaluated to get the y values at the endpoints, and of course also at the points that I found in number 1, and I just compared my values. Now that might not be totally clear, but when I do the next example, I will make it abundantly clear. But the thing that has to happen is this algorithm is only valid if you can't use it if you have any points in this interval where the function doesn't exist. For example, There would be no problem applying this little algorithm for this function because it exists for every x. I would find the y value for -3. I would find the y value that goes with 10. I would find the derivative, find the local maxes, local mins, and compare the y values. So there's no problem. One could do it here. I'm not going to. One could not do it here because x equals -4, the function doesn't exist, and that's one of the values, and so the algorithm won't work. In this case, the function doesn't exist at x equals -4, but because it's not a value in this domain that's declared, this would be perfectly acceptable, and you could go through the algorithm for that function. Here we have two values where the derivative doesn't, where the function doesn't exist at plus or -3. -3 is a value in the interval here, so you could not use this little algorithm to determine extreme values. I'm going to replace this function with a different function. I believe the worksheet that you have would have this function in its place. So this is example 3, and this will be the neatest and cleanest way to illustrate the algorithm. The new function that you guys have that I didn't bother to print up on my page look like this. Now, in fact, this function is taken from the textbook. It is one of the examples in 3.2. I'm not going to do all the steps and show the work, but trust me, the derivative works out to be this function. And we are asked to find all the absolute extrema on the interval from 0 to 14. Now, the function doesn't exist at -2, but that doesn't cause us any problems because the interval that we're investigating, that's not a part of it. So what I do is I take the extreme value, I let x be 0, and I work out the y value that pairs with that, and of course that works out to be 8. I take the second value, the other endpoint, and I let x be 14, and I get 14 squared plus 2 times 14 plus 16 divided by 14 plus 2, and that works out to be 15. Trust me, it works. I took it from the book. Now over here we look at the derivative. We put it in factored form. We don't worry about the -2. We only worry where does the first derivative equal 0, simply at x equals -6 and x equals 2. Now the derivative equals -6. The derivative equals 2 in, and that is a part of this interval. So we are going to check this out. But where the derivative equals 0 at -6, because that's not part of the domain that we're investigating, we basically can just ignore it. We don't care what's happening because it's not in this section of the graph that we're looking at. I merely have to find the y value for this one value, which of course is going to be 2 squared, 2 times 2 plus 16 using the original function. And what I'm going to get is the number 6. So these were the two endpoints. This was the one value where the derivative equals 0 that was in the section of the function that we're investigating. Clearly, the absolute max value is the number 15, and the absolute minimum value is 6. This is the algorithm. Find the y values for the endpoints, and find the y values for the points where the derivative equals 0, making sure, of course, to only consider points in this interval. And it's easy to tell which value is your max and which value is your min. The last example I'm going to do, which is example 4 on your sheet, is interesting in the sense, there's your original function, which of course is quite an unusual function as far as we are concerned. But what I'm going to do is take the derivative, which is 3/5 x to the -2/5. Now remember, that basically means I have an x in the denominator now. Now the algorithm says find the y values for the endpoints, and find the points where the derivative equals 0. But here, the derivative never equals 0. You're not allowed to replace x with 0. And this fraction would never work out to equal 0 regardless. So basically, that just means you find the y values solely for the endpoints. When I put -2 into the function, I'll use my calculator. And again, you're going -2 to the 3/5. You're going to get approximately -1.5. And when you put 3, you're going to get the approximate value 1.9. So clearly the absolute min is -1.5, and it occurs when x is -2. And the absolute max is 1.9, and that occurs when x equals 3. At the bottom of this handout, you will see the homework, which is from the textbook. It won't take you that long. Let us know if you have any questions. Have fun.